Our next video on torque, we're going to take kind of a two-dimensional view of torque and really focus on the equation torque equals force cross radius. Alright, so in this problem we have an 8 Newton force that is applied to this wheel. So let's go ahead and write down that our force is 8 newtons. To figure out our radius, we always have to count from somewhere, and this problem says we want to answer each question relative to the center of the wheel. So here's the center of the wheel, and we need to count the radius. Now the radius is actually has to be measured perpendicular to the force. So I think the best way to do this is draw something called the line of action. So the line of action is the line that goes directly through the force. Now we're not going to count from the center to the force itself, but we're going to count to the line of action. So the radius will be measured this way. So in this case, noting our scale that each one of these boxes represents 10 centimeters, our radius is going to be 20 centimeters. That gives us a torque of 160 Newton centimeters. And then it asks us for the direction of torque. So in the last problems with the seesaw, if you watched that video, we talked about whether the torque was on the left side or the right side of the object. Well, torque is really measured as clockwise or counterclockwise. So in this case, imagine this being a wheel. We're pulling from here, and we're taking the top side and moving the top side to the right. That is going to cause this object to spin in this direction. So our wheel spins this way, which is the clockwise direction. Alright, so let's go ahead and take a look at another example. So in this case we have a force of 6 newtons. Let's draw our line of action. Remember, our line of action should go directly through the force. Our radius is measured from the center directly to the line of action, and again those should always be perpendicular. This is called a cross product. So in this case my radius was 10, 20, 30, 40 Newton or 40 centimeters, excuse me. Again, remember that scale that every one of these boxes represents 10 centimeters. That'll be consistent throughout this lesson. That gives me a torque of 6 times 40, or 240 Newton centimeters. This time we're pulling upwards on the right side. Since we're pulling upwards on the right side, that'll cause our wheel to spin this way, which is the counterclockwise direction. Alright, another similar example. So in this case we have an 8 Newton force that is applied to the left. Before I get my radius, I want to draw my line of action. So my line of action again goes through the force. And I'm trying to figure out, okay, what is the distance from the center to the line of action? Well, in this case, the line of action goes right through the center. So that means our radius is going to be 0 centimeters. And our torque is going to be 0 Newton centimeters. What this means is that this force is actually not trying to rotate our wheel. So it's just pulling to the left, but since it's on the far left side, our line of action went through the center. And our torque is not trying to rotate us in either direction. So anytime our torque is 0, our answer there for direction will be neither, and neither will only be the answer if the torque is 0. Alright, so let's move on to a different type of problem. So in this problem, we're asked to calculate 4 different torques and the net torque. So let's start by drawing a line of actions. I'm going to do them a little bit darker on this problem. So here's my line of action for force 1. So my distance from the center to the line of action right there was 10, 20, 30, 40, 50 centimeters. And I get my torque by doing torque equals force cross radius. So I would do 50 times 3, and that gives me 150 Newton centimeters for torque 1. This time, since we're pulling down on the left hand side, that's going to try to make this spin in this direction, and that is the counterclockwise direction. Let me erase that line though so it doesn't throw us off. Alright, for our next one, for force 2, let's go ahead and draw the line of action directly through the force. Now you'll notice the line of action goes through the center. That gives us a radius of 0. So no matter what force 2 was, 5 times 0 gives us 0 Newton centimeters. And neither. Alright, drawing our next line of action through force 3. So counting from the center to force 3, we go 10, 20, 30 newtons. 30 centimeters multiplied by 6 newtons gives me 180 Newton centimeters. Force 6, or force 3, the 6 Newton force, is trying to make this spin this direction, which is clockwise. Alright, and lastly, for force 4, we have our line of action there. Our radius would be 10, 20, 30, 40. And 40 times 4 gives us 160 Newton centimeters. Since we're pulling up on the left side, that's going to cause a counterclockwise rotation. Alright, so my last thing I need to do is to figure out the net torque. So this is where it becomes really important. We're not really looking at the sides like we talked about in the seesaw problem. We have to look at the directions of the torque. So I'm going to combine any torques that are in the same direction. So in the counterclockwise direction, I have, so I'll call this torque counterclockwise, I have 150 plus 160, and that gives me 310 Newton centimeters. And clockwise, I only had one torque, which was 180 Newton centimeters. That means that I have more torque counterclockwise, and I can do, to get my net torque, how much more torque is pulling counterclockwise than clockwise. I'll do 310 minus 180, and that gives me 130 Newton centimeters counterclockwise. And what this means is if all these forces were pulling at the same time, this wheel would spin counterclockwise because there's more torque acting counterclockwise. Alright, let's take a look at another problem. Let's determine all unknowns that will keep the wheel at rest. Alright, let's start off by calculating any torques that we know. So we'll start off with force 2. So force 2, I'm going to draw my line of action, count my radius out to the line of action. So 10, 20, 30 centimeters. 30 centimeters times my force was 10 newtons. So 30 times 10 gives me 300 Newton centimeters. And that would be causing a torque in this direction, which is clockwise. Alright, next. Well, I don't know either of the other two forces, but I do know that one of the torques has to be 0. So if this is where I'm counting from, then I know that force 1 is at the center, And so I don't know the force of 1, but I do know that the torque for force 1 has to be 0, because its line of action goes directly through the center. So 0 and neither would be my answer there. Alright, I also know that I want the wheel to be at rest, so that tells me my net torque has to be 0. So if the wheel's at rest, the torques have to balance. So 0 and neither is my answer for the net torque. So that means I know that torque 3 has to be 300 Newton centimeters counterclockwise, because I need the torque clockwise and the torque counterclockwise to balance each other. Alright, so for torque 3, let's take a look at 3. I'm going to write down force, radius, and torque. Well, I know that torque has to be 300 Newton centimeters. The radius I can count, so if I draw my line of action, I can count that my radius out to the line of action is 10, 20, 30, 40, 50 Newton centimeters. And just like we do force times radius to get torque, we'll do torque divided by radius to get the force. So 300 divided by 50 gives me 6 newtons. By the way, I just noticed a little mistake, is that my radius is just 50 centimeters, not 50 Newton centimeters. Alright, so I know that force 3 must be 6 newtons. And for force 1, well, if the wheel's at rest, but right now we've balanced the torques. So if the torques balance, that means no rotation. But the wheel's not moving up or down either, or in any direction. So if the wheel's at rest, the forces also have to balance. So if I have 10 newtons pulling downwards, I need 10 newtons pulling upwards. I already have 6 newtons pulling upwards, so I need another 4 newtons pulling upwards. Alright, one last problem right here. So in this problem, it says we need to figure out the torque caused by this 7 Newton force, but this 7 Newton force is pulling at a 27-degree angle with the horizontal. Alright, anytime I see a diagonal force, what I want to do is I want to break that down into components. Alright, so labeling my sides H. My angle is theta. I always know my angle touches my adjacent side, so H, O, and A. I can go ahead and use the equation A equals H cosine theta, and O equals H sine theta. So I get my horizontal component would be 7 cosine 27, which gives me 6.24 newtons for my horizontal component. And for my opposite, my vertical component, I'm going to do 7 times sine 27, and I'll get 3.18. Alright, so if I think about each one of these having a line of action, let's start off with the adjacent side. So the horizontal component has a line of action that goes right through the center. So basically what this tells me is this horizontal component, this 6.24 newtons, is not trying to cause any rotation. It's not causing any torque. So let me go ahead and erase that. So I don't need to use that 6.24. But my vertical component, the line of action doesn't go through the center. The line of action is actually 10, 20, 30, 40, 50 centimeters away from the center of the wheel. So for my torque, I'm just going to look at the component that's perpendicular to that radius. So I can do 3.18 newtons times 50 centimeters. And I get 159 newtons. Alright, again, the adjacent side isn't causing any rotation, it's just the opposite side of the vertical component that I need to look at. So that vertical component is pulling up on the right side of the wheel. Pulling up on the right side of the wheel will cause a counterclockwise rotation.